you can probably tell by my accent that I'm not North American, like my two colleagues. In fact, I'm European. But I might not be tomorrow. So, I'm very pleased to be here. Thank you very much for inviting us. It's really, really exciting to see so many people who are interested in quantum computing, and I hope that you'll find this, the whole of the presentation very interesting. So, if this is going to start getting a little bit more technical now. I'm going to run through some of the hardware before Denny looks at the programming aspects. And we'd very much like you to understand what we're talking about, so please don't worry about interrupting, and I'll do my best to answer the questions, and if I can't, then I'm sure Denny can. Basically, Bo put this slide up before. And really, the essence of this is the idea that we really need to try and close our minds to everything we've ever done in computing. In a computer program that we write today, then everything we do is very linear. We do a task, we might put something into memory, we go and do another task, and so on and so forth. And that's completely not the situation with the D-Wave architecture. Within our environment, we send a quantum machine instruction that Denny will tell us about later. We send that to the machine, and it's very much an analog type process for that landscape to be formed that Bo showed you earlier on, and for that landscape to then provide an answer in a very, very short amount of time to the problem that we pose for it. And it's trying to take our real-world problem and map it to the quantum computer. That's the essence of everything that we're working on today. So if I go on to the next slide, the devices itself, this is our laboratory in Burnaby, which is a suburb. It's very close to Vancouver, and we probably have at any given time about 18 quantum systems running in our laboratories, and you can see 3 of them here. And they're about 3 meters square and then 3 meters tall. And they're that size so that people can actually get into the working environment and work at them at the same time. So the 3 boxes or the 3 racks that are in front of that, the first one is the interface, the server that actually controls and talks to the processor, to the computer itself. And the other 2 contain all of the infrastructure to run the dilution refrigerator and keep that going with the helium and the nitrogen that's involved. So if we then were to look inside what goes on within that device, we can open the door and have a look inside. And we actually see here that the exploded view that we had before is actually encapsulated in a number of cylinders to make sure that each process of dropping the temperature is kept within a vacuum and kept away from the other temperature as we drop it to that very low 15 millikelvin, sorry. So this is a little bit like a Russian doll affair, whereby if you imagine that we have these plates here, and I think I can hit the button to, where's my pointer? About there? No, that's not very good.
That was very bad.
That was very bad. Am I right back at the beginning? Yeah. Can I move this? Okay, all right. So I will get there. Denny, you're going to tell me which is the laser button on here. This is not mine. Is it that top one? Yeah, okay.
That button right there.
Fabulous. Good. So the picture that I was showing there starts at the very top, and that's about room temperature. And then each of the plates as we come down is lowered to the next stage of the cooling process until we get right down to the processor at the bottom, which is down here. So you can see these plates. These are all the different temperatures that we come through by doing different types of refrigeration, be it the temperature of liquid nitrogen, and then later we use an isotope of helium to bring the temperature even lower. So you can see what sort of mechanical problem this involves. This is as I'm sure from a physics lab point of view, starts off as a relatively standard dilution refrigerator that will do those sort of temperatures for cryogenic type of research. But in those sorts of environments, then the end temperature or the end environment doesn't have to be as delicate as the quantum one does. So from our point of view, it's a really mechanical challenge, an electronic challenge, to get the signals that originate down in this processor here, to get those all the way back and back out to the outside world as the solution to our problem. And whereas you can imagine that in a traditional computing environment, then any bit of electromagnetic interference that might change bits within the environment, we tend to call that noise. We might have things like jitter, but effectively it's jiggling and moving some of the data. From a quantum computing point of view, our noise is heat. So if any heat comes down those electrical wires that are actually coming down to the processor to actually set the problem here, that noise is a major problem for us, as is electromagnetic interference, vibration, and those sort of things. So it is a very, very delicate environment that we need to establish. Having said that, because of the fact that we use so little power, and we take a little bit of chilled water to run the system, other than that, we could actually sit the device here. We don't need a specialized computer room to put it in. The major consideration probably is the vibration. So here is the actual quantum computer itself. This is the housing that it's housed at down at that low temperature. But you can probably just make out that this part here is actually the processor itself. And I have a wafer here that we produce them. And if I can I pass that to you? And if you want to pass that round. This wafer is actually an experimental fabrication that we did. And on there you'll see two shapes or two sizes of squares or processors, one of which is the 1,000 qubit system that's available today in these devices that we have in the laboratory. And we also did the experiment to see whether we could actually print and fabricate the 2,000 qubit system. And right now, since that wafer was made, which is probably about 6 months old, then we actually have the 2,000 qubit systems running in our laboratories, and we're doing tests on them. We've had to do some modifications, and we've now got the new set of wafers back, and we're going to continue. And as Bo said, the 2,000 system should be available in about a year's time. So what is really quite interesting here is people who have keen eyesight will be able to see on that wafer that actually the large square is actually subdivided into unit cells. And these unit cells have 8 qubits on them. So you can... I have big thumbs, you know? So this is our unit cell. And I've represented here 2 qubits, the red rectangles. So if you imagine, for us, a qubit is effectively a circle of semiconductor, niobium superconducting material that obviously takes no power. And so what we tend to do is, to make that unit square, we stretch that circle of superconducting metal into one of these long rectangles. And obviously we stretch in the other direction as well. So we end up with a lattice, a 4x4 lattice of qubits. So this will represent 8 qubits within the unit cell. And where each of those qubits touch, then that is where they have interaction with another qubit. So Denny will explain more about this in his programming environment, but if you can imagine that this qubit here is it can take a position of either being the 1 or the 0 in that superpositioning environment. And we apply a weight to that qubit that's part of our program that says, ideally, we would like you to be a 1. So it then considers that idea and says, shall I be a 1 or shall I be a 0 when the actual solution is read? And that qubit then is then influenced by the qubits that it connects to and qubits that it might connect to in the next unit cell. So as you can imagine, there's a sort of like a force field of energy that's happening here. And if you imagine you multiply this up to 1,000 qubits, then the number of possibilities that we're searching through is the huge number of 2 to 1,000. So that's just a number that you probably can't even imagine. But if I were to tell you, or perhaps even remind you, that the estimated number of particles in the entire universe is about 2 to the 300. So the permutations and possibilities that we're searching through in that landscape are a number that's over 3 times the number of known or estimated number of particles in the universe. So moving on from the sort of the hardware environment, and this is sort of like an introduction to what Denny's going to talk about from the programming point of view, then on the left-hand side, I'm demonstrating what a classical computer would look like. And here, we're saying the fact that what we're trying to do is a floating point instruction. And as Bo described, floating point instructions are exactly what a classical computer has been designed to do. Really, it's a series of transistors. From those transistors, we build AND and NAND and OR gates. And from those, we build subtraction and multiplication and addition units. And therefore, we get the ability to do floating point instructions. And if we wanted to do an optimization problem or a Monte Carlo sampling environment, we then build layers and layers of software on top of that base operation of the processor. And so this would be our program, our Fortran program, to actually make that optimization problem possible. With the actual the D-Wave quantum machine, then what we've actually designed is something that does optimization. So the actual bare metal, the actual silicon itself is wanting to do optimizations, and it doesn't need any software to do that. That contrasts with the idea that if we wanted to do a floating point operation or to do some arithmetic on a quantum computer from D-Wave, then we would have to build in lots of layers of software to enable that optimization problem to be translated into an arithmetic problem. So Denny might mention the fact that we've done sort of the experiments to see how could we add numbers together, how could we factorize numbers and that sort of thing. And it's possible, but it does take a lot of effort, and you end up losing some qubits to do that. Okay, I'm going to hand over to Denny at this point. Oh, I'm doing that one. Are there any particular questions about the hardware?
Excuse me. How do you connect the qubits on these 8-qubit slice? How do you connect the slices between them, one to each other?
So from the unit cell itself, yeah. Do you mean? Okay. So within those connections, obviously there are overlaps that are within the unit cell. And then at each end of each qubit, there are connections to the next unit cell.
What kind of connections?
Presumably that's an inductive connection, Denny?
Are you asking about the nature of the physical device that connects the qubits? There's a mutual impedance that's controllable through a Josephson junction located at the intersection point. So we can control whether the two spins want to be aligned or anti-aligned and the extent to which they want to be that way. It's honestly, you're asking a device physics question. None of the three of us are really device physicists.
Yeah.
And so if this is not a satisfactory answer, we can put you in touch with somebody in Burnaby that can give you a nice, complete answer.
Okay.
What it does bring up that I didn't mention was the fact that within those unit cells, if you imagine that the horizontal qubits are connected to the next unit cells, and the vertical ones are connected to the next ones, then if you haven't noticed by now, the ones in the middle don't actually connect to anything other than qubits within their unit cell. And that then leads on to the programming of how we have to look at each qubit and program it